Myself, that's better. Hello everybody, I'm going to start the meeting, the lecture now, or the virtual excursion right now. Everyone hopefully can hear me. Yeah. Okay, so this is a virtual excursion rather than a lecture. So we're going to take a little tour around the southern half, or the southern quarter of Islay. We're going to start and finish in Port Ellen, and we're going to go along the coast and come back to Port Ellen where we'll finish. We're going to go and visit lots of things on the way. Let's see if my screen will change. Here we are. Someone says there's an echo on the line, yeah? I don't know if everyone's getting that. I am talking to a microphone, so it should be okay. All right. What's that annotation? Okay, so Islay, we're off the west coast of Glasgow, off the west coast of Scotland, obviously, west of Glasgow. Everyone knows where that is. Everyone's been there. Let's just see, people are chatting here. What they're saying? It's okay, right? Okay, so the sound's fine. Fine. Okay, let's head off. A quick look at the stratigraphy and the map of Islay. Most of you are very familiar with this. Most of you have been on a trip with me before to Islay. If you haven't, we're going to be down in the south corner here. We're looking at the rocks that are perhaps the youngest rocks on Islay. You can see here we've got a stratigraphic column on the left-hand side here, and the sort of rocks on Islay generally tend to get older in the west and young going towards the southeast. There's a big anticline in the middle called the Islay anticline, where rocks of the Jura quartzite, the yellow, are folded right over in a big fold. But on the south part of Islay, we are on the southeast limb of the Islay anticline, where the rocks pretty much are dipping southeast, and the further southeast you go, the younger the rocks become. So it's a fairly simple sort of geological picture. In that we're in the Dalradian, so we're talking about rocks that are around about 650 to 600 million years old, and the rocks we're going to be seeing today are in the stratigraphy are up in this part of the section, which is sort of in the Argyll group above the Jura quartzite, locally the Easdale Crinan subgroups of the Dalradian. So we're the youngest rocks. We're seeing the youngest rocks on pretty much the youngest Dalradian rocks on Islay. Obviously, there are younger Dalradian rocks further southeast, but these are the youngest ones we see on Islay. Just to put it in perspective as a stratigraphic column with the sort of lithostratigraphy outlined here in this column here. So we are looking at rocks in the sort of formations. All these formations are obviously were built and named after some of the main rock formations in there. So we're looking at things like the Port Ellen phyllite and the Lefroy quartzite and the Ardmore grit up in here, which lie above the Scarborough conglomerate and the Jura slate, which are the sort of equivalents of the Easdale slates on the mainland. So this is the same as the Craignish phyllite or the Adrasheg phyllite. So this is the sort of stuff that we're seeing, and it's all sort of slightly younger, or maybe simultaneously with the Tavalic volcanics at about 600 million years. So that's where we're at stratigraphically and lithologically. Someone's trying to talk to me. Oh, or they're going to mute themselves. James's iPhone. Do I need to mute? Okay. Okay, I'll carry on. James's iPhone, are you trying to ask me a question, or you want to mute yourself? Right, I'm going to mute everybody except me. Okay, if you need to talk, please let me know by putting it on the chat. I'll look at the chat to see if you've got anything to say. All right. Okay. Let's. You've shown this slide before. Yeah, I'm not really pumping the book, but there is a book. I'm going to be covering bits of excursion 11 and 10. They're in the existing book, and in the new book, I've got 2 excursions in the new book, which we're going to be looking at tonight. So this is really a dry run of of a couple of excursions I've got in the new volume. Now, just as a precursor to this, I'm not an expert, and these localities on here, the research has been done by others. I'm the facilitator and the teacher rather than the researcher. So you can ask me hard questions. I probably won't be able to answer them, but if you ask me a hard question, I'll defer it to people like Alistair. I think actually Alistair's online. He said he wasn't going to have to go out to dinner, but I think he's online. I gave this talk a few weeks ago to the Edinburgh Geological Society as a sort of a post-AGM we chat. But I thought it could go to a bigger audience, and we have a bigger audience than the AGM of the Edinburgh Society. So I'm glad everyone's here, and hopefully you'll enjoy it. I'm going to take you on, as I say, a virtual tour of the south coast. We're going to look at some of these localities here, a lot of them related to distilleries. So we have Port Ellen over here, where we are sitting right now. You've got to suspend your reality, and we're going to be moving from Port Ellen along the coast up to here. We'll nip up to Kildalton, then we'll be driving back. We'll stop for lunch at Ardbeg, and then we'll finish in Port Ellen. If we get time, we'll go to Kilnorton and look at some unusual minerals over in Kilnorton. I don't know what this annotation here. Oh, I got it right. Close that. Okay, so let's head off. We're going to just, first of all, I wanted to just introduce why I've picked these localities, and these are conservation review sites that were published in the PGA about 7 years ago, 2013, by a whole host of experts on the area. These are the people that have done the real work here. People like Jeff and Dave Stevenson and Jack Tragus. They are the experts in this area, and these papers in the PGA are well worth reading. There's a whole series of them. I think there's about 7 of them with an introduction that cover all these sites, about 80 sites across Scotland that are sort of key conservation review sites for the Dalradian in Scotland. So we're going to actually, 4 of them are in this are on South Islay, and we're going to look at Kilnorton. That's why I want to go to Kilnorton. Cerneg Farm, which is actually Lagavulin. It's not called Cerneg Farm anymore. We're going to go to Ardbeg, and we're going to go to Listry Bay. We'll also have a quick pop up to here as well. Yeah, this is the introduction paper. So these papers are well worth reading, and the GA have done a great job, and I think they should promote it a bit more because it's really good work. Yeah. So let's head up a little bit to the north. We've driven up here. This is right up in the far northeast part of this coast, and this is Kildalton. Kildalton has a lovely 8th century Christian cross, and like many of the monumental stones in this part of the world, they're made of what, if you read the literature, called epidiorite. Now, epidiorite is a crazy term, really. It's not really a diorite. It's a metadolorite or a metagabbro or a metabasalt. We're not quite sure of the grain size of it because it's metamorphic. So a metabasite is probably a better term, and you'll hear that used a lot this evening. Metabasite being the sort of this. So this is a sort of part of one of these igneous, now metamorphosed igneous sills that we're going to take a look at this evening. The Kildalton Cross is a good place. You can see here on the sort of aerial photograph here how the stratigraphy or something is being picked out in a linear fashion here, and these high ridges and low little glens that trend along the strike of the Dalradian, but the ridges are made of this metabasalt, metabasite sills. Yeah, and they form a bit higher ground and lower ground here. This low ground that goes right into this little bay here. I wanted to just take you to this bay very quickly because we can zoom into it very quickly tonight. Because this is Glas Uig, little bay, very remote bay, and this is one of the few places where in World War I, German U-boats landed and rustled sheep and took on water because it was a very sheltered, remote harbour on the west coast. So this is one place where German soldiers wandered around and surprised a few estate workers with a few sheep on their backs. So it's an interesting little part of the world. Now let's go do some geology. So we're just heading back, having got up to Kildalton, which is up here. We've just headed back a little bit down the coast, and we're going to go to this place called Listry Bay, which is just here. On the geological map, you can see here we've got a sort of bright green blob here, which is what we're going to look at first, which is a tertiary or Cenozoic Paleocene age igneous intrusion. And you can see here, these are the sills, the mesobasite sills intruded into a succession of mainly sort of quartzitic sandstone sequences here in yellow, and over here in more metamudstone rich lithologies and some conglomerates. And this is the Jura quartzite. So unfortunately, the colors mean that it's all, anything that's yellow is quartzitic, anything that's bluish is carbonate, anything that's grayish is sort of metamudstone. So it's fairly simple. And the greens are the igneous rocks, and the bright green across it, cutting across it, is this younger tertiary intrusion, which we're going to have a look at right now. So here we are at Ardilistry Bay, just having a quick look across the bay at Knockronistal, which is which forms this intrusion that I showed you on the map. And we're going to sort of park our van in these woods here and have a look at this intrusion. So there's a wee sort of detailed geological map of the bay. We've parked here in our minibus or whatever, and we're going to do a couple of wee walks. One to see the intrusion in a couple of in a locality at the coast here, and then a couple of old little quarries. Come back to the van, grab a drink or sandwich, and we're going to go and then walk the coast around to these 3 or 4 localities on the sort of north side of the bay. We're not going to actually climb the hill, although if you wanted to, you can walk up to here, up this little track, fight through the bracken and go up to the top, which is a lovely place to go. If you do, this is the view. This is when the bracken's down a bit. So this is the view of the locality, Ardilistry Bay, with the localities on the peninsula here in the tertiary intrusion, and then the localities over here in the Dalradian metasediments and meta-igneous sills. As you can see here, the sills sort of form these skerries and reefs going out to sea. It's sort of treacherous navigation, but brilliant place to go sea kayaking and hiding around and exploring, and it's just full of otters and seals and wildlife, and it's a great place to be. So here's a wee map stolen from Martin Hall's work in Preston. They did a lot of work on this intrusion. They believe it's quite an important place to study differentiation of a basalt. I'm going to talk a bit more about that. It's going to be it's an unusual intrusion because it's got a lot of late stage differentiates with some unusual mineralogies. And the bulk of this intrusion is formed of what they call a leucodolerite. We're going to show you that in a minute, which is a light colored dolerite, not quite the sort of dark, sort of brown, rusty colored dolerite that you traditionally associate with some of these Cenozoic dikes in the Western Highlands. This one's much, much lighter in color, and it has a teshinite core to it, which is an analcime rich dolerite type rock, and then it has a sort of cyanite, which is much more evolved rock in this quarry here. Now the exposure is not great, so there could well be more of the cyanite in here. So we're going to have a look at the main dolerite down here. We're going to look at the teshinite here, and we're going to look at the cyanite in the quarry here. So this is, we walk down the road from our cars. We're going to cross through this gate into this lovely green field where the quarries are in here. And then we're going to go down to the coast at the end of the peninsula. When we get to the end of the peninsula, we find this sort of rounded boulders of this sort of brownish, rusty coloured rock. And this, every time you see this colour of rock and this sort of form of rock in the Western Isles and the Western Hebrides, you know it's almost certainly a dolerite, a tertiary dolerite. The fact is here that it's huge. I mean, normally these are in dikes that are 1 or 2 meters thick at the most, sometimes up to 10 or 15 at very, very most. But this is huge. This is a couple of 100 meters wide, and it's, as you saw on the map, it's at least 1 kilometer, 2 kilometers long. It's a sort of big blob, and it's quite unusual. If you take a hammer to it and open it up, it's very, very light color, which is what it means. Leucodora means light colored dolerite. And it's got quite a lot of plagioclase, quite calcic plagioclase, and northite 70%. It's got augite olivines in it, and a lot of sort of crystallization textures that suggest that the plagioclase crystallize first. Often these olivines and augites and the pyroxenes crystallize first in many intrusions, but this one seems to have plagioclase, and it may already be a differentiate from something more mafic, something with a much more olivine in it. The chilled margins certainly seem to have more olivine in it, and the olivine is much more magnesium rich with a high sort of forsterite content. And a lot of this is believed to be quite anhydrous. This is a good example of if you've got a big volcanic complex, you've got a lot of meteoric water kicking around, a lot of reaction between the magmas and water in and around volcanoes. Whereas this looks like it's an intrusion that's probably never reached the surface, so it's never sort of seen rainwater or meteoric water, and it's just the only water in it is the water that was in it anyway, the sort of deuteric water that was already in the system. If you move a bit further north into the quarry, you find this little scruffy quarry. You think, well, what's all this? Still sort of brownish rock, but it's quite fine-grained. It's a bit darker, and it's got it's a dolerite, but it's got quite a lot of plagioclase in it, which is a lot of it's converted or secondary conversion into an alcime, which is the sort of key mineral that distinguishes a teshionite from a normal dolerite. And they reckon that the guys who've looked at this in detail reckon that it's synchronized crystallization of the minerals, and the analcime is replacing plagioclase, and it may just be a slightly later intrusion. It may just be a sort of little blob that's come up into the center of the body in some way, and it has a little bit more water in it, which is what's causing the analcimization of it. So there may be, but this may be water that's already in the magma, deuteric water that's already in the magma, rather than introduced water. So it's a sort of closed system. So it's quite interesting that that we're seeing differentiation of an olivine dolerite without any extra things thrown in. It probably hasn't reacted much with the country rock, and it hasn't reacted much with any water. So it's just doing its own thing. It's sort of I think someone told me that it's like simmering in its own juices. It's sort of sitting in underground, maybe 2 or 3 kilometers, maybe a lot deeper underground, just simmering away, cooking away. We come out of that field, there's the gate. There was a car crash a few years ago, and it seemed to knock this wall down, but the wall's rebuilt now. But locality 3 is, as usual for most geologists, we love going into scruffy quarries, crossing over barbed wire fences and fighting bracken and branches in these overgrown quarries. This one's no exception. You could just glimmer a bit of rock in the background of this quarry. It's a bit of bushwhacky, and this is a good part of this was in the autumn when it was down a bit. That if I went there now, you'd probably not get into it. The rhodius are growing in it as well. So, but when you get to the rock face, you do find a rock, and it's much lighter. It's got some sort of striation or foliation in it, some rubbly appearances here. It's sort of a strange sort of looking rock. And you look at it in detail, it's got all these little black minerals. It's quite light, and it's mostly plagioclase, but it's got some potassium feldspar and some nepheline and some amphibole, and it's classed as a nepheline syenite. So this is an evolved rock from the dolerite. It's also got some weird titanium minerals and some weird zirconium minerals in it. It's got carsutite. These little needles are the carsutite, the titanium mineral. It doesn't have any olivine in it, and has a high zirconium agerine pyroxene, and some very rare another calcium zirconium silicate called catapleite, which is these are very unusual zirconium minerals that are quite rare. It's probably quite a small amount. They call these nests. It's little pockets, pods of this cyanite that's just sort of like the scum on the top of a boiling pot of jam or something like that. It's just the sort of stuff that got left over at the end with a bit of water, and and some of the heavy mafic minerals have dropped out, and it's got this sort of lighter, more felsic sort of crystallized mush that's crystallized at the very end and you get little sort of nests, little pods and little veins of this thing here. It's the only known occurrence of zirconium agerine in the British Tertiary Igneous Province, and it's only the second known report of this catapleite zirconium calcium silicate in the literature. And there's also some very high REE enhancements in some apatites in it as well. So a mineralogist's dream. But a lot of the mineralogy is quite microscopic. It's not beautiful collecting material here. Yes, you can pick up this with a few 5mm blades of the unusual pyroxene. And then you get this sort of the carsutite I did say it's actually reacted as an amphibole, because it gets this titanium ophedronite around the rims of them thing here, and there's the analcime. This is a thin section from stolen from another from the people that did a lot of this work. And this is a sort of high resolution SEM scan of one of these crystals of the aegirine, and it's got zonation in it. There's the aldite, which is an alcine, and it's got this little minerals of this catapleite in here. But you can see it's microscopic, so this is not going to be a museum specimen you can collect, but it certainly just highlights the unusualness of this little exposure. And I drew this little picture just to sort of try and give you a sort of feel for what the sort of what a stock or a boss is. It's like this is like a dike, a big dike that perhaps never reached the surface, sort of like someone said it was like a big zit or something like that. You know, it's a big pimple underneath your skin, sitting there and differentiating itself. Whereas a lot of them just hit the surface. Maybe they even become a fissure volcano, these dikes, and some just taper out into sills and don't have a distended head. So a distended head of a sort of a small boss or a small stock is the sort of way it's probably. We think the current intrusion erosion level is not far off the top of the intrusion. You go to the summit of the hill, there's a lot of horizontal sort of jointing and layering, so it's quite possible that what we're seeing at the current erosion level is not far off the top of the actual intrusion. And we think that the belief is that the leucodolorite was first. There was a later tessionite, and then you got little pods of cyanite coming in at the end. And the differentiation is controlled by this original. You get olivine and plagioclase settling out first, that enriches the remaining fluids in the more felsic minerals. And it has it's pretty much one episode, and it hasn't had much interaction. There's no partial melting of the country rock or anything like that, or incorporation. There's no xenoliths of the thing, so it wasn't a very forceful intrusion, ripping off bits of country rock, incorporating them, melting them, or anything like that. But a nice little place to go. And as I said earlier, not linked to a central intrusive complex. So we're seeing all these things are just what happened within that magma as it came out of this hypothetical magma chamber. It didn't react with any water. This volcano could have it rained on it, and have water could all sort of mix up with here. But this thing is no hydrothermal interaction with the magma. So that's why it's got little alteration. It's quite interesting. So there's the hill. There's the little peninsula where we've been. That little quarry is there. We're going to walk back to our car here, and then we're going to just cut through the woods here, across this beach, paddle across the Burren, then look at a few localities along here, ending up at this sill at this far distance here, at the far end of the bay. So there's the geological map yet again. So we've just done 1, 2, and 3. We're back at the car. We're going to go through the woods, cross the beach, and look at these sills as we go along to number 6. There's a sort of a view across the beach. There's the hill. We've just come through the woods here, come through this gate, cross this beach. There's a nice burn to paddle in here. On the beach, there is actually a whole line of boulders of dolerite. This is actually a typical Islay dike, a couple of meters wide of dolerite, normal sort of dolerite. And I have no idea how it relates in age to that. They're obviously very similar age, but which one is first, I don't know. And why we get dikes. This is standard sort of northwest, southeast orientation of dike. But here, there's a dike here, just at virtually the same place as that photograph, the first locality, that's trending at right angles to it, and with a lot of spheroidal weathering. But this is also another dolerite dike, but it's sort of intruded at right angles to the one that was that way. But what's interesting here is that this is the first of our Dalradian sills that we're going to be talking about for the next wee while. And there's a sort of foliated sort of, or banded sort of rock here. If I go around the corner, you see it a bit better. There's the dike. That spheroidal weathering is actually just in here, and the dike is in here. And then you get this sort of foliated sort of rock here, and then it's less foliated as you go up through into this lichen-covered mess up here. And if you look at it in detail, you can see that a lot of this, it looks like metasedimentary rock. It looks like a sort of cleave metamudstone, but it is actually part of an intrusive dolerite that was altered. And we're going to talk quite a lot about alteration of dolerite sills as we go on through this field trip. And we come round the corner of that intrusion. There's another one here, and at the top of it, you get the top of the sill here. It's sloping towards me, so it's we're coming this way. We're sort of younging as we walk this way. You have to cut through this one here, and you can see here it's got this is the sort of country rock it's intruded into, which is sort of bedded sort of meta sandstones and meta mudstones, and the top of the sill has also a foliation. And the reason it's foliated is because of fluid flow. The center parts of these sills are, well, the sills are inclined by the deformation, but the center part of the sill is unaltered. So assemblage A of the mineralogy in the center of these sills is unaltered, and it's unaltered green schist. It's obviously altered in metamorphic terms from its original plagioclase and pyroxene, just like we saw in the dolerite on the hill. And it's now at the center of this hill is a green schist facies epidiorite, if you want to call it that, of amphibole, epidote, and albite. So that's the center of the sill. Zoning coming out of the core of the sill, you get a lot of calcite replacing the amphibole and epidote. And on the outside is this assemblage that's calcite, quartz, and chlorite, which is all being formed from metamorphic fluid flow coming up out of the metamudstone. So the clays are the water's coming out of the clay minerals in the metamudstones. There's a lot of carbon dioxide coming out from, because all these metamudstones are quite rich in carbonaceous material. So you get a lot of water and carbon dioxide. It's reacting with the sill mineralogy to change it from an amphibole and epidote to calcite and quartz and chlorite. So we get a very different sort of mineralogy, even though it's all originally the same material in this particular sill. And you get a zonation that's often asymmetric. So we just saw that in that sill, that the bottom bit was quite a lot of the altered stuff, and the top bit was quite thin, and that's because these sills were probably inclined at the time of the main fluid flow. So the main fluid flow may well have been slightly post the main tilting and the deformation of these rocks, and it's asymmetrically altered the sill as the fluids have come up and been deflected by the sill margins. We're going to see more of this. We're going to see a lot more of these sills, and we're going to look at other features of that. But I wanted to just show that one early on because it sort of sets the scene for what we see in some of the other sills. We do need to. This reaction of basically the calcium and the carbonate coming out of originally coming out of the amphibole and epidote, turning into chlorite and calcite, is something that is referred to as carbonation, and it needs carbon dioxide and water to do it. And it's certainly syn deformational, and it may even be slightly post syn deformation, and it sort of outlasts the peak deformation. So it's carrying on as these metamudstones release their bonded water in these clays, and as the clays minerals in here move from illites and smectites into chlorites and muscovites, they're releasing water. There's graphite being formed, and it's producing carbon dioxide, which is moving in here and reacting. That's the key thing. And here's a picture of an amphibole crystal that's being sort of carbonated. It's being replaced. You can see the whole thing here. There's the edges of the amphibole, and it's being replaced by the calcite and some micro quartz in here as well. So the amphibole, this is like, so the calcite in a way is pseudomorphing the amphibole crystal. So you get this blob of calcite, which often when they're weathered, these calcite blobs weather out into little pockets. So you end up, it looks like a limestone with little pockets of weathered out calcite, but in fact it's an igneous rock that's been metamorphosed, which looks then like a sedimentary rock. So it's got something for everybody in it. As we go up through this sequence, geologically we're in the Lefroy quartzite, which tends to be a sort of quite a sort of well bedded. It's got some it's got some little cross beds and things in it. It's a sort of probably some sort of shallow marine quartzitic sandstone. There are mudstone beds as well, but they're very poorly exposed because they tend to be in the low ground. But there are these little sort of interbeds of sandstone in the Lefroy quartzite. And you come in another sill here. So it's about the third sill we've crossed over, because we're aiming to get to this big sill here that forms the sort of the southern end of the bay. And when we get there, we come around the corner here. So we're looking at the sill end on. We've just come over all this territory here, and we're looking at the rocks here. And it's a lot of tumble down rocks here, but it's quite a thick sill. And the interesting thing at the bottom is that at the bottom there is a different sort of rocks to the rocks in the middle and the middle at the top. We get the schistosity, the sort of foliations at the top and the bottom, but the bottom, it seems to be it's just dominated by metapyroxenite. Now, metapyroxenite means it's a metamorphic rock that was once pyroxene. So it's metapyroxenite. It's now amphibole, because that's now green schist metamorphosed amphibole. So it's basically a rock that's, the bottom of this sill is basically a rock that's nearly 100% actinolite. And then there's then there's a quite thick 3 or 4 meter thing with large plagioclase in it, which were quite calcium-rich plagioclase, now metamorphosed to an anorthosite, and then we get the metabasite with relic phenocrysts above it. So when you look at it in pictures, this is not a very good picture of the metapyroxenite, but it's quite a lovely rock. It's quite a lot of sort of shimmering. You can see all the crystal cleavages and things like that. So it's got a lot of actinolite in it. The metal has huge plagioclase. These are sort of centimeter-sized plagioclase phenocrysts in it, and then at the top we get a sort of thing with probably slightly smaller phenocrysts in it. But there's sort of some lovely rocks to sort of look at. Again, it's covered in lichen, seaweed, and boulders and things. You tend to find that the nice-looking rocks are the ones you can break open with your hammer. They're actually in and around. And these rocks, I've taken pictures of these rocks down here, but the sequence has been established by Jeff Tanner and co. And this is a beautifully layered sill intrusion. Now, most of the sills are never that thick that they actually accumulate the heavy minerals at the bottom. So the pyroxenes would have crystallized first and dropped to the bottom of the sill, and then leaving the rest of the sill more plagioclase enriched. So this is an example of a sill that was not homogeneous at the time it was then metamorphosed. It was already layered and then metamorphosed. So two things have gone on here: igneous differentiation, slightly different to the one we saw, the tertiary one. With that again, differentiation is a key process that's happening in many igneous rocks. As I say, I'm not an igneous petrologist. I don't get into the detail of it, but nevertheless, I see what I see. And it's an interesting intrusion here that has been metamorphosed. Okay, so we've done enough hard work here. We've legged ourselves back to the van. We've driven back down here, driven 2 or 3 kilometers back down to Ardbeg. We're going to get a nice coffee in the lovely distillery cafe. And while we're there, some of us are going to walk out and have a look at a rock over here. So here's the cafe in Ardbeg. Nice whiskey too. There's one of the GCR sites is here, just on the sort of northeast end of the distillery. Now, I'm only going to take you there very quickly because I've been there once or twice and I still haven't really got to grips with it. This is the Lefroy quartzite that it's sort of the succession that we're in, which is interbedded sort of meta sandstones and meta mudstones with a nice sort of cleavage in the meta mudstones. There's a sill in here, just to the left of here, and when you look at it in detail, it's got sort of pinkish sort of patches in it, and these are a mineral called stilpnomelane, which is a sort of biotite, a very iron-rich sort of biotite, and it's very unusual in these rocks to find this. This is actually a thin section of that rock with the stilpnomelane. This is just a Wikipedia type snatch grab of it. It looks like biotite in thin section, but it's much darker. It's the same pleochroism, but it's much darker and a lot more iron rich. So it may be that this sill this particular part of this sill is enriched in iron. Now, it's very unusual, but it's very difficult to see. This stuff I should have put a scale here. This stuff is a couple of millimeter at most. So they're very small crystals, but it's an unusual rock, and and Jeff has rightly pointed it out as a place that we should know about and preserve. Yeah. So we've just quickly had a look at that because we're going to move on to some another wee walk at Lagavulin. So this is Lagavulin Bay. There's obviously the distillery, and Lagavulin Bay is sort of guarded by these dolerite sills, metadolorite sills, forming the headlands here of the little sheltered bay. And this is Dunyvaid Castle, which we'll have a look at as well. And over here at Cerneg, or it's now Gus McPherson's boatyard, over on the other side of the bay. So there's the map. I was just showing a picture taken from over here. There's the bay. You can see here that the igneous intrusions in the dark green here are forming the high ground here. They also form the high ground behind the bay here, and the bay is formed in the more eroded out sort of meta mudstones and meta sandstones of the Lefroy quartzite area succession, and the sills stand out as higher ground around it. And we're going to do 2 little walks. One, we're going to park at the distillery, walk along here, down here, look at this bit, walk back, then just walk. We may even drive to here and then have a quick look. There's the boatyard. We'll climb, look at some rocks down here in the sedimentary meta sediments, and we'll look at the sill here as well. So locality 1, which is just on the northeast side of the bay, you get the metabasite sill again, but this time it's intruded into some into some meta sandstones, and there's very little foliation at the bottom of this sill because there's very little mudstone available with its water. And the clay minerals in the water. So basically we find that a lot of these sills in this part of the succession don't have that characteristic foliation. This is a nice little locality because we've got the Dalradian metabasite sill with its base here. You can follow it down through here. And then there's a tertiary dike, a metre or so thick, just running straight through the middle of the bay and standing proud. So you've got two intrusions here, a 600 million year old one and a 60 million year old one. And there's a fault along through here which follows the coast, and it follows the coast all the way along here. And there's another big tertiary. This is probably 5 or 6 meters wide, going out into the sea. It's quite an impressive dolerite dike going out into the sea. And there's Duniveg Castle, and you can see here. This is, if you were mapping this, you can see that the high ground is the sort of area of the meta-dolerite sill, and the low ground is these the meta mudstones and meta sandstones. And you can see here, we can actually get into one of these little gullies, and you can actually see the contact here. And this is, so there's very little foliation in the sill here, and very little alteration, because you've got basically a quartzite sequence here, and then straight into the dolerite or the meta-dolerite. With very little, and this has got some cross bedding in it. There's very little deformation, very little foliation, and very little contact metamorphism as well. This is this fault that runs along the coast, right through the middle of the metabasite, bit of quartz veining in it, and you can see it quite prominently on the aerial photographs. You can see here we were just at locality 1. We just sort of looked into that little gully there. It cuts right along here, and it's an obvious feature on the satellite photographs running this way. And it seems to offset that dike. So there's the big dike, the sort of 5-6 meter wide one I was showing you. There's that little thin one we saw right at the beginning. This is this bigger one in here. And there's the fault, and maybe it sort of cut slightly. Maybe there's been some sort of dextral movement on that fault that's just offset it slightly. It's a vertical fault, vertical dike, so it's got to have to be offset by. So there may be some offset here. This is Duniveg Castle. Have a look at them. I'm just going down here. Have a look at number 3 down here. So there's the base of the sill again. There's our dipping interbedded sandstones and metamudstones, and there's Duniveg Castle itself. And again, it's on the main part of the castle is built on the sill. I wanted to sort of just digress slightly into the archaeology and history, because I know some people had enough igneous and metamorphic petrology by now, would like a bit of history and archaeology. So this is an artist's impression of what it looked like. There's the high ground, there's the castle keep on the top of the high ground of the sill, and on the lower ground, sort of to the north, there was a sort of enclosed area with a sea gate. A lot of this has been excavated and is being currently excavated it would have been excavated this year, and it's been every year for the last few years, and for the next 10 years, Islay Heritage, mainly run out of Reading University with Stephen Nathan, are excavating this to try, with the help of Lagavulin. Maybe in some stage in the future there'll be a nice visitor centre there, sponsored by Lagavulin, to show you all the beauties of this castle. There's the aerial view of it. There's the excavation going on. They're excavating this bit here. There's a sort of map of the area. So that picture I showed you was here. This is looking down on all these other structures. There's the hall on top of this top of the sill. The key find from a year or so ago was this Campbell seal. It dates from 1590, I think. It's something like that. And it was a lead seal for pressing into wax the sort of certified documents. So this is a castle this part of the castle is sort of 14th, 15th, 16th century and younger, but it may have had much earlier history than that. So Stephen's team are quite interested in excavating this castle. It's never been done before. And they say it's close to the distillery. It make a nice little visitor complex if more found. This is a key find, but there's a lot more to be found here. It's never really been looked at. So we've left Duniveg. We'll head back. We'll go and have a look at some rocks on the south west side of the bay. And here we are on the southwest side of the bay. We're going to have a look at these rocks here. We're standing on top of a sill, but it seems to have stopped, and there's either a fault here or it's just a blob, and there's another blob on the other side. So I'm not quite sure how the geology actually works here, whether it's just faulted out or whether some of these sills just stop and start again. We get down onto the coast, onto the rocks. We see again this sort of interbedded sort of sandstones and metamudstones. You see the metamudstones carrying some sort of foliation in them, and you get into the detail of it. And you see metasandstone with the bedding into the metamudstone band, but the cleavage in here, there's a cleavage in it. It's a good place to demonstrate bedding and cleavage to students. And also, this metasandstone bed seems to have some sort of hypothesis thing going into the rock. Like I've labelled it as a D, so it's a little sedimentary dike going into this metasandstone below it. And the key thing in this locality that we've come to see, that why it's a GCR recommended site, is this beautiful sedimentary dike that's folded. So here's a bed of sandstone here that's unfolded, and then you get this like a snake. You can walk this, and it's just like a big snake. It sort of comes in and out, in and out, in and out, in and out, and it goes on. You can see beautiful folds in it, yeah. And it goes for about 16 meters. Now, I don't know whether it goes up or down, but it's a sedimentary dike that's been intruded into the metamudstone sequence here. There's a thick metamudstone sequence here, which has been deformed. It's carrying a cleavage, and a lot of the cleavage is axial-planar to some of these folds. So some of this folding is undoubtedly enhanced by the tectonic deformation that obviously postdated the sedimentation. But I suspect this dike was never a linear feature in the first place. It would have been a sinuous feature in the first place, and some of the folds in it, or the sinuous bends in it, have been amplified by later tectonic deformation, because you've got quite a thick mudstone unit here that's going to get deformed more than the more competent sandstone beds. And I drew a little cartoon of what this may have looked like. So here's the sea, here's the mud, and then there's some sand bodies here being deposited, just hypothetically, yeah. And you put more and more sediment on top of it. You bury these sands, and maybe they're trapped. I've drawn them as sort of lensoid, because maybe they've got a lot of water in them that isn't escaping, and the water's trapped in it. Then you need some sort of trigger, like an earthquake or something, yeah, that then sugars the whole lot up and fluidizes the sand and water in these sand lenses, and it shoots up or down. And I need an expert to tell me whether they think that they would predominantly. I would imagine it wants to go up because of buoyancy things, but the way that this has been described by Jeff Tanner is that that this dike goes down. It goes down from its mother bed rather than up from it. But it needs a bit more work. But as I say, this has all been tipped at 30 degrees now and deformed at greenschist facies, so it's a little bit more difficult to try and ascertain exactly what happened. But that's the sort of feature we're seeing, a sort of a mother bed of sand that's then attached to through a dike, an intrusion. So we've seen dikes and sills of igneous rocks just in the last 2 or 3 localities, but here we actually have a dike and a sill feature in sedimentary rocks. So it's just this, as I say, this locality, this field trip today is something for everybody: sedimentology, metamorphism, igneous petrology, the lot. So it's a lovely locality. It's a beautiful thing. And also at this place, just about 50 meters away from from the dike, is a dike. But this dike is a subvertical. Not quite sure exactly its orientation, but it certainly seems to be pretty vertical. But it's made of, instead of the tertiary dolerite, this is actually the 600 million year old metabasalt, metabasite thing. It's got a bit of schistosity. It's a bit altered. And it's certainly of the same rock as the metabasite Dalradian sills, but it's a dike, not a sill, and they're very rare. I only know of 2 on Islay, and this is one of them, and the other one's just around the corner from me. We're going to look at it in a second. The northern Jura has a few of these things, and I'll come on to that in a second when we look at the second locality. But these are vertical, north-south trending dikes, which probably fed the sills. So the sills are subhorizontal, well, they would have been at the time of intrusion. These dikes would have been subvertical, and these are maybe feeder dikes to the sills in the succession. And we're just going to climb onto the hill overlooking the boatyards down below us here. There's the distillery. There's Duniveg's on the other side of the bay, on top of the hill here. Nice little climb up to the hill, nice viewpoint. There's an old Brock wall here. This is there's not many good Brocks on Ireland. This is about as good as it gets. There's another one up on Brookladdy, up behind Brookladdy, but this is 2,000-year-old walling still there. There's not much of it, but it's a nice place to visit anyway. And if you look down to the summit into this gully, you see another one of these schistose dikes. So you can see the schistosity quite nicely in here. You can see a fabric in the thing here, yeah? And it's sort of cutting through, and it's actually eroded out in this sort of gully here. And this is north-south trending as well. So how did these dikes form? Well, I used a similar picture to try and illustrate that as well. So this is the igneous rock, green. Yellow one was sandstone. This is igneous rock, it's green. So dike comes up, and probably a pressure balance here between a lithostatic pressure and the overburden pressure and the pressure in the magma. But it reaches a certain point in the sedimentary succession, and it spreads out. These are dikes, these are sills and dikes that are being intruded at the same time that the sediments were being deposited. So these are young wet sediments, yeah, and the intrusion is coming into the wet sediments, reaches a certain level, and then spreads out. Yeah, time goes on, a bit more sediment gets piled in, another pulse of magma comes up, hits the same sort of pressure point, and then spreads out. Yeah, and as the succession gets more and more mud and sand in it, this keeps going. This process keeps going. So it looks like the sills are progressively younging to the southeast, and they're fed by rare examples of these dikes. Yeah, and we've just seen two, and they're the only two I know of on Islay. But that's probably how what we're seeing here. Then, of course, this is all. I should have shown it, but this has all been then tipped at 20 degrees that way, so that you can imagine this tipped over, which is why we're getting those sills like a sort of scarp and dip sort of escarpment sort of feature. But these sills are probably related to the Tayvallic volcanics, which have been dated at about 600. So this gives us some sort of feel for how old this is. These sediments are being deposited pretty simultaneously with the intrusion of these 600 million year old sills and dikes. If you go to North Jura, just a digression, but North Jura has a whole host of these. In fact, there's very little sills, it's all dikes. And the view is that originally when they were first mapped, they were thought, because they cut through the dip, the rocks here, the dips of the Jura quartzites dipping this way, these are vertical, it was thought they were younger than the deformation. But their geology, their mineralogy, their petrology is all consistent with them being exactly the same. They're the same metamorphism as the sills. But the whole of North Jura and Skava has got north-south dikes, which are probably the feeders to the Tayvallic volcanics. So, which are stratigraphically younger than the Jura quartzite, obviously. They're over this way. So this gives us some idea about what was going on in the, and it tells you if you've got a trend of these dikes, they will be at right angles to the tension directions, or so it tells you something about the extension directions, and that's what this work by Colin Graham and Graham Borrowdale did in the 80s, where they tried to sort of suggest that the extension direction was, in fact, everyone thinks it's northwest southeast. It's probably that way. It's probably southwest northeast extension going on, because you take the dip out, you rotate those around, they actually would go that way. Yeah. So you've got extension going on in a roughly sort of north-south direction, which fits nicely with Roger Anderton's work he's done on the paleocurrent directions in the Skaba conglomerate and the ECL slates, which he also suggests there was a flow from south to north. As well, so it all sort of fits. Tells you this. So the igneous petrology is telling, and metamorphic petrology is telling you something about the passive margin of the Dalradian, how it developed and what direction it developed. This is a cartoon that we've put together in the past, sort of showing how the Dalradian passive margin developed from a sort of a pre-rift sequence 800 million years ago to a sort of a much more mature sort of rift 700 million years ago, and by 600. We actually were getting intrusion of basaltic material, an oceanic crust developing, and maybe what we've got here, we're in some sort of small basin that sort of maybe strike slip control or something, or some sort of feature that maybe there's more high ground, more continental crust outboard of us, and we're still fairly inboard on the margin. But nevertheless, we're in this sort of area here where we're getting the crust is thinned. Extension has progressed to the crust is thin, and allowing basaltic material to intrude into the crust, into the new sediments, and form these sills and dikes at about 600. So that's sort of a overall model. How are we doing for time? Okay, we're just about right. Just going to climb up the hill behind Port Ellen, before we go down for a drink, have a look at some of the rocks over at this part of here. This is the ferry coming into Port Ellen. You can see again, we've got this topography related geology of the sills going out here. The Calmac ferry has to come along here, come right round a big marker buoy over here somewhere and come in through a little gap in them. So not a great place for a Calmac capfin. I don't like it in rough weather, especially when it's a southerly, blowing a hoolie from the south. And but it's a nice shelter bay once you got in it, because the geology shelters you from it. This is the maltings for the distilleries. And here's a geological map of Port Ellen, and we're going to quickly look down at one locality here in this excursion. I'm not going to do the whole excursion. We're going to drive to here, park here, and have a look at this little bay here. Alistair Skelton, I think he's online. I haven't checked. Takes all his students here, so he's going to interrupt me if I talk rubbish here. But he takes all his students here. This is the Ard. Again, you can see the stratigraphy, the topography here with the sills and the intervening metamudstone units here. That's the Freud distillery in the background, and Texa over in the island over there. One good way of doing it is take a sea kayak, and there's a guy on the island that takes you sea kayaking, and you don't have to buy any of the gear. He takes you out there, and you can go and look at these skerries and these dikes and sills and otters all at close hand, and it's a great way of seeing the rocks. Here's an aerial photograph of the southern part of the Port Ellen, and we're going to visit on foot. Going to visit this little bay in here, which I call Alistair's Bay, because it's where Alistair always takes his students, and he takes them to this little exposure here on one of these little bays here, and says, "Here's a sill, and here's some metamudstones here. Where is the boundary?" Someone talking to me here. Oh. Alistair just saying thank you. All right, so yeah, here's his metamudstones here, and this is definitely igneous, ex-igneous rock, metabasites here, but where do you put the boundary? Yeah, and the hammer's the clue. It's also a distraction, because if you say it's where the hammer is, you would be wrong. But you're all experts now, because you've seen this foliated margins of the sills now, and you know this is not sedimentary rock here, though it looks like a schist, a sedimentary schist. You know that the boundary is not there. It's here, and this is the altered bit. This is the foliated. It's a good, nice. Alistair takes people here because the exposure is so good and clean, and it's wave washed, and it's not covered in too much biology. So we've got metasediments here in the sort of yellowy color. The margin, the altered margin of the sill here with its schistosity. The reason it's got schistosity, it's got a lot of chlorite in it. Remember we were talking about how the epidotes and the amphiboles are. The amphibolin here is changed to chlorite and calcite, so you get lumps of calcite, which are weathered out in little pockets, and a lot of chlorite, which is carrying this foliation here. And there's little weathered out little calcite pockets in detail. So it looks like a sort of calc schist. It is a calc schist, but it's actually not a metasediment. It's a meta-igneous rock. So I'm not going to go into the detail of this again. We've covered it earlier, but this is the completely altered bit, the partially altered bit. Remember I told you the zonation, we had a sort of A, B, and C. This is so this is a beautiful example of this zoned, altered sill here, yeah, with the no calcite in the middle and lots of calcite in the outside. It's also a good example of a sill that's been interacted with seawater. At the time, remember I was saying that these sills are probably intruded into wet sediments close to sediment water interface. So these sills weren't homogeneous either. So that we've seen a sill earlier on that wasn't homogeneous. It had a peroxenite sort of cumulate layer in it, and this one, like many of them, have got big lumps of plagioclase in the middle of them, and also some of these plagioclases are zoned. This one's got a calcic core, and it's reacted with seawater. The plagioclase reacted with seawater, which takes the calcium out of the plagioclase, and it turns it into a more sodium plagioclase, like an albite, and creates a lot of epidote, which we're going to see in a second. But sometimes the cores are retained, and then they've been certainly later metamorphism, which affects the calcium plagioclase. This is protected by this albite layer. You get a lot of epidote, and here's some epidote veins. You get these sort of pistachio green veins of epidote. There's a volume change when you epidote production. You get these segregations with this sort of tradition, very, very sort of pronounced sort of it's not really a cleavage, it's a sort of parting in these things here, and you can see them quite nicely in this little cliff here. You can see all these little epidote segregations on veins and pods and things like that. So this is a good example of spilitization, where the sill has been affected by seawater, and there's been an exchange of sodium and calcium to reduce the calcium plagioclase to a sodium plagioclase and create epidote, which is the green stuff. Yeah. And there's a nice picture stolen from Alistair of the sort of metabasite here with its epidote vein. There's the epidote, and what's happening, the sodium's coming out and the calcium's going in from there. So the calcium's coming out, the seawater's going in, taking the calcium from the calcium plagioclase here and producing epidote. Bit more techy, but this is basically what's going on. So we get albertization of the plagioclase, releases the calcium. The calcium gets moved into amphiboles and epidotes, which contain calcium, and you get these patches and segregations of epidote. Yeah. Then we get metamorphism. So this is happening pre-metamorphism. This is metasomatic type reactions that are happening pretty much at the time of deposition. So this is 600 million years. You get this at 470 at the metamorphism and the foliation development. You get metamorphism of the sill, tilting of the sill. Some of the chlorites and amphiboles are being realigned. And then you get the metamorphic fluid flow of these clay minerals in the phyllites and the carbonates coming through here, breaking through these segregations of air. You get a sort of metamorphic front forming, and you get this carbonation. So Alistair's team have done a lot of work on this carbonation reaction, and they used it to look at how fluid flows through these rocks in different ways and how much carbon is produced, or carbon dioxide is produced relative to weathering. So looking at the net flux, you can do a lot of fancy maths calculations on advection rates and try and work out how much carbon is being released in orogenesis. So it's quite an interesting sort of take on metamorphism. Metamorphic fluid flow is a very interesting feature of metamorphism. It's not just about the mineralogy that's left, it's about, well, how do these fluids move through the rocks, and what effects have they done, and how do they affect the carbon cycle, which is obviously of prime importance to us these days. And just some pictures from Alistair's papers of some of the way that the fluids might flow through some of these rocks here. So in the center of the sills, these big phenocrysts are protected to an extent, but the fluid still gets through on the cleavage planes and starts to change some of these plagioclases, and amphiboles can be generated in the middle of them. You get some amphiboles where they've been turned to chlorite, where the fluid flow has come through the minerals, and he describes this as intergranular flow. And the sill margins, a lot of the flow is intergranular, because and it's also evidence that some of this foliation was developed early, and the fluid flow is a bit later, because some of the chlorites that we're replacing in these big plagioclase pseudomorphs, the chlorites are unaligned, unlike these ones. So some of this fluid replacement of these big phenocrysts is later than the deformation. So it starts to tell you in a little bit more micro detail about the interrelationships of fluid flow and deformation histories. So it's quite an interesting sort of area to look at. And this is what we call a PT diagram. This is pressure up here, temperature on here, and it's sort of low pressure and temperature. We actually get the sills placed in the layers. So there's low temperature and low pressure. Gets buried a little bit more. We get the spilitization, the calcic plagioclase replaced by albite, and the segregations happen. Then the deformation happens, yeah, and then we get this carbonation as things sort of cool down a bit. We're still at fairly high temperatures, but the pressure's reduced maybe a little bit, and we get this carbonation going on with the infiltration of the water and carbon dioxide fluids, and sort of infiltration of the hydration of the margins. So, and then excumation, and then probably later on in the late Paleozoic sort of veining and sulfide veins coming in as well. So which we're not going to look at today. But yeah, a sort of nice PT, sort of a typical PT diagram of a deformation going on. So, right, we're nearly at the end of our excursion. We're perfect timing. Got one little locality to go to, because we've then Port Ellen here. There's where we were, just down at Alistair's Bay down here. And we're going to just nip around here very quickly, park our van here, and walk about 20 meters to have a look at this locality here. It's the last of the GCR sites on the south coast of Islay. So I put it in because I sort of just to complete the set. Here's a geological map. It covers a bit bigger area, but it's the Jura quartzite here we're looking at, and this is the Port Ellen phyllite that we've been, and the post and the Jura and the Scarborough conglomerate and the post Jura quartzite succession here. So we're down a little bit lower down in the succession here, at the top, very top of the Jura quartzite, and there's a locality here by the lighthouse, which is on Scarborough conglomerate. This is what it looks like on a windy day when you wouldn't want to be on a ferry. But on a nice day, you can walk across this little track here and cross this little bridge here and look at the Scarborough conglomerate here, but you couldn't do it today. So this is a little bit higher in the succession. Looking back, the lighthouse is just over to the left here, and there's a little track to it, and you park here, and there's some dipping Jura quartzite in this area here. And Jeff describes these rosettes of on these little bedding plains, quite micaceous bedding plains, in a sort of more metamudstone rich part of the top of the Jura quartzite. You get these beautiful blades of and sort of rosettes of blades of crystals, and the interpretation of these is that they are ex-kyanite. They're kyanite crystals that have been pseudomorphed by pyrophyllite and other sort of later minerals, but basically they are kyanite, blades of kyanite that are sitting there. And there's several the original interpretation of this was that this just happened to be kyanite. It's not what you'd expect in the greenschist facies in a quartzite at the greenschist facies and metamorphism. The kyanite occurs in much higher grades of metamorphisms. This is, if you find this, you would just be, it's very unusual. And the interpretation, it can be, there's probably two interpretations here. One is that the mineralogy of this little bed of rock is very, very high in aluminium, and that has sort of enhanced the ability of kyanite to grow anomalously. The other one is probably there's a lot of carbon dioxide kicking around as well. So there's a sort of twofold thing. You've got a sort of perfect storm of a crazy mineralogy and a bit of and some CO2 rich fluids kicking about as well. That have caused this development on these bedding plains. So it's a very unusual and it's a beautiful locality. The problem is that someone's gone and hammered it and taken the lovely best bit away, one of the best bits away here. That picture of Jeff Tanner's was taken there, and my picture was taken from that block, and you see someone's chiseled it out and taken it away. So it's already well having conservation review sites and publicizing them and telling people to protect them, but if you publicize it to the wrong idiots, they go and wreck them. So it's a shame, really. Nearly at the end, some people ask, why are there so many distilleries on Islay and the south here? The reason is that this is a good place to hide distilleries, and the geology dictates the landscape, and these little ridges and furrows and things were a lovely place to hide the stills, and these ones that remain here are the ones that became legal. Yeah, although they were the bigger ones with the bigger owners and the more money, and they rather than little farm distilleries, and they survived. But this area was probably chock-a-block with illicit stills, and I believe, though I've yet to get it proved to me, that a lot of these early distilleries, in the farm distilleries in the woods here, would have used charcoal rather than peat, because it doesn't make any smoke, and you could hide away from the authorities and brew and distill your stuff. I put this in because it just shows where all the water's coming from. All the water in these distilleries comes off the Jura quartzite locks, and it comes down here, and it's incredibly soft. But this one here, this has got a slightly higher humic content because it sits in a boggy lock, whereas the other ones come pretty much straight off the hillside straight into the distilleries. And there's a new one coming here, which I always worried about where it was going to get its water from, because everybody else has pinched all the water. But I believe they've got a little burn and going to have a reservoir, and they're going to sea cool it rather than use the water. For a lot of this water is actually used for cooling the stills, and so Farkin is going to have a seawater intake, which is a bit like Kalila, for those that know something about Islay distilleries. Okay, I pretty much reached the end of it. A lot of these little talks I've been doing are on the ScottishGeology.com website, and this one the recording of this will go onto this website too. So the ones, if you've missed any of my previous ones and loads of other stuff, it's on here. It's all done by the Scottish Geology Trust, which you can give money to if you want to, or you can join the Scottish Geology Trust. So in terms of sort of preserving and enhancing and promoting geology, if you hit this button here on the Scottish Geology Trust, you'll get to the old website with the ScottishGeology.com website, And in the resources section of that, you'll find all these videos that I've been doing. So support the Scottish Geology Trust. It's a new venture and deserves our support. Thank you. Time for a dram, and mine's an Ardbeg, please. I'm going to probably just, if you want to ask a question, just unmute yourself and talk away, yeah? Or use the chat. Anyone, any questions?
Yeah, it's Ian here, David.
Hello, Ian. Yeah.
Yeah, wondered why the sills appear as kind of ridges. You know, they seem to be coming in lines all the time rather than in some sort of. I thought they might be flat or.
Well, they're tilted up, so remember they're intruded into the succession, and the whole succession is dipping 30 or 40 degrees to the southeast. Generally, there are small folds in it, but so basically they're tipped up, and it's more like a sort of scarp and dip, sort of cuesta sort of landscape. Yeah.
Right. Okay. Oh, that makes sense.
So you're seeing the sort of eroded, truncated edges. I should have drawn it as a cross section, but yeah, that's what you're getting. It's horizontally. It was horizontally bedded with the sills and the sediments. Then it was tipped 30 or 40 degrees to the southeast, and then truncated off. Yeah.
Good. Thanks.
That makes sense. Yeah.
Yep.
I'm just looking at the chat line here. See what's. So Con Gillen says kyanite doesn't. Now Alistair's team have looked at this. I mean, I know that Alexander has looked at this. Alistair, do you want to ask about pyraphyllite and kyanite?
Yeah, sure. The reason we think it's kyanite is because we can see it. The kyanite's not gone. You see kyanite cores pseudomorphed by porphyllite, so it's definitely kyanite. The fact that it's making radiating structures means it's struggling to grow, which is fairly reasonable given the low temperatures.
Yeah, and it's in quite a sort of thinly bedded sequence of
yeah. It's a super aluminous rock, and if one looks at an AFM diagram, it's perfectly reasonable to have kyanite there, but it's not going to have an easy time, which is why you get those really, really strange stellar structures.
So, Con, does that answer your question? I know you've posed it. Is that because you've asked if you don't normally see it in clusters. Does that? But if it doesn't answer your question, you can have an offline discussion with Alistair about it.
Colin's asked a very fair question: is there a publication on this? And the answer to that question is that Colin Graham started writing the paper in the 70s. I continued after 2000, and my student continued in the 2010s. And no, we still haven't published it. So my sincere apologies to the community.
Right. But Alexander's done it in it's part of his PhD, isn't it? Now
he hasn't published it.
No, but there is something in his PhD about this, yeah.
There is. And it's time for him to publish it.
Right. Okay.
He's not done his job right there.
Andy Moffat said he's seen stellate kyanite in Shetland, yeah. So obviously it's not just here. He's seen it sort of in sort of star-shaped features in. Yeah, Con said, is there a publication on this? Alison's just answered that question, that there might be. I mean, it's described nicely in the Jeff Tanner 2013 PGA article. It's described, but the metamorphic petrology and the fluid reaction stuff is all in Alexander's PhD. That's possibly available on Ethos. I'm not sure you can maybe find it. I don't know.
I can send that to anybody who asks.
Okay, so Con, if you want to get a hold of Alistair, and he can send you Alexander's PhD. Yeah. Good reading. Right, well, I'm going to get a dram. Anyone else got any other questions? It's not an Ardbeg. My Islay stash has run out. I'm going to Islay in 2 weeks' time to replenish the stash. So, cheers. Did that make sense, Alistair? I didn't tell you anything too rubbish, you know.
The talk was excellent. It was really good. Thank you very much, Dave.
Okay. Yes, and it's
I would love to have
it's
a
funny
brand.
talking about somebody else's work when that somebody else is sitting in the audience. It's quite nerve-wracking, but
You did it far better than I've ever done. It was really good.
okay, right. Well, cheers, everybody.
Cheers, Dave.
All right. See you in Islay. I'm going to be there soon, so hopefully you'll get there soon yourself. Yeah.
I wish.
Mm.
Scotland won't even let us Swedes in yet. We're apparently contaminated.
Okay. All right.
Thanks, Dave. Have a good one.
Okay. All right. I'll end the meeting if there's no other questions. We'll leave it there. Yeah. I'll go and finish my whiskey.
Thanks, Ed.
Okay. Goodbye, everybody.